All right, so we're going to start the next part of chapter 4, and that is about discrete distributions, and we're going to look at a special type of distribution. So we saw in the last part that we have these discrete distributions that we list out all of the outcomes along with all the probabilities. For instance, we flip 3 coins. And we saw that, well, there's either 0, 1, 2, or 3 heads on those 3 flips. Now, it turns out that this is a special type of distribution called the binomial distribution. And we're going to look at some binomial distributions. We're going to see, first off, how would we come up with these probabilities in a binomial distribution case? And also, we're going to look at a shortcut for finding the mean and standard deviation when we have the binomial distribution case. So what's a binomial distribution? Well, it's a probability experiment. So a binomial experiment is a probability experiment which has 4 different points. The first point is that a binomial distribution has to have a fixed number of trials before we start the experiment. So for instance, on our coin flip example, we started saying that we're going to have 3 flips of the coin. So we fixed the number of trials at 3. Now, each of the trials is going to have 2 outcomes. And that's also a characteristic of the binomial experiment. Each trial has 2 outcomes. On the coin flip, it was pretty obvious that those 2 outcomes would be like heads and tails. But in general, we're going to call those 2 outcomes success and failure. So success is when we get what we're looking for. Failure is what we get, is what we're getting when we're getting something we're not looking for. Now, the third point of a binomial experiment is that each of the outcomes are independent. So when I'm flipping a coin, each flip is not going to have an impact on the outcome of the second flip or the third flip. So outcomes are independent between the number of trials. And then lastly, the probability of success on each trial stays constant. That's kind of also similar to the outcomes are independent, but we're looking for constant success. So for instance, if we were rolling a die, we'd say, well, if success was the number 2 on the first roll, the second roll, success wouldn't be evens. It would still be the number 2. Hopefully that makes sense. You'd have constant success each time. Now, whenever we have a binomial experiment, that leads us to the binomial distribution. And when we have a binomial distribution, the notation that we're going to use is special. We're going to use lowercase p for the probability of success for each trial. The lowercase p is going to stand always in a binomial experiment situation for the probability of success on each trial. Lowercase q is going to be the probability of failure for each trial. Now, because we only have either success or failure, these 2 probabilities have to be complements of one another, and therefore they have to add up to 1. So if I know the probability of success is 50%, then the probability of failure also has to be 60%. Or excuse me, did I say 50? Let me back that up. If the probability of success is 50%, then the probability of failure has to be 50%. If the probability of success is 25%, if we have a 25% chance of success, then we have a 75% chance of failure. So hopefully that all makes sense. So P and Q are complements of one another. Now lowercase n, just kind of like it's always n is usually my sample size, well that's the case here too. It's kind of like a sample size. It's the number of trials I'm doing. So again, if flipping 3 coins, n would be 3. And then x, the number of successes, well, x can be anywhere from 0 up to n. And that was sort of evident in that last probability distribution that we saw. That if you flip if you flip three coins, you might get 0 heads, you might get 1 head, you might get 2 heads, you might get 3 heads. You can't get 4 because that's too many, and you can't get any negative numbers. So x is always going to be a whole number between 0 and the number of trials we have. So we already kind of mentioned this, but when we identify notation in our coin flips where x is the number of heads, well, n is going to be equal to 3 because we're flipping 3 coins, so 3 trials. Our probability of success, well, success is getting a heads, so on a single flip, the probability of success is 1/2, or 0.5, depending on whether you want to write that as a fraction or a decimal. So number of heads, success is 0.5, or 1/2. And the probability of failure would also be 0.5, or 1/2. So that's the notation for flipping 3. And when we've identified the notation, what we're really meaning is the n, the p, and the q. So n is equal to 3, p is 0.5, q is 0.5. Now this was something we saw also in earlier chapters. We had this, according to 2015 Pew Research, about 6% of Palestinians have a favorable view of ISIS. And we said, well, what is the probability that if you select 5 Palestinians, you find at least one who has a favorable view of ISIS? Now, recall what we said about this. This was way back in the independent multiplication section. We said, well, that 6% stays constant the whole time. Notice that we're going to select 5 Palestinians before we start. So we're selecting 5. That 6% is going to stay constant the whole time. And so fixed number of trials, outcomes are independent, probability of success stays constant. We have a binomial experiment going on here. Now, once you see this, once you say, oh yeah, we're selecting 5 and 6%, once you see this, you'll see that binomial experiments happen all the time. Now, let's again identify this notation. Well, since we're selecting 5 Palestinians, that means that n is equal to 5. So n is equal to 5 in this case. And because our probability of finding one who has a favorable view of ISIS is 6%, our probability of success is 0.06, or 6%. Whichever way you'd rather write that, as a percentage or a probability, is fine with me. Okay, on the if you're on the test, 6% or 0.06 would be the same. So probability of success is 0.06. And probability of failure, therefore, is 94%, or 0.94. Again, whether you write that as a percentage or a probability is fine with me. Now, one thing I do want to mention that some people get confused on, remember, success doesn't mean that it's a good result, right? Here we're saying we want to find one Palestinian who has a favorable view of ISIS. We call that a success. That's not necessarily a good thing, but that's what we were looking for. So if we're looking for that, that's why we call that a success. We're looking for one who has a favorable view of ISIS, and so our probability of success is 6%. It turns out this was also a binomial experiment. The one where we looked at the percentage of people who are side sleepers, or the number of people who are side sleepers if we choose 5. Push pause and then identify the notation on this. All right, so hopefully you check that out. This one, fairly straightforward. N is equal to 5 because we're choosing 5 people. P is equal to 60% or 0.60. And Q would be 40% or 0.40. Okay, and we can see that the number of x's can range anywhere from 0 to 5. Now, question pops up is, well, how do these probabilities come up? You know, back in the coin flip example, we could have listed out all of the different sequences. Well, that's how you should think about probabilities here, all right? What if we wanted to find the probability that 2 people are side sleepers? Well, what would we do? Well, hopefully, again, notice that 60% of people are side sleepers. So each success has a 60% chance. Each failure is going to have a 40% chance. Now we're going to choose 5 people and we want 2 to be side sleepers. So what we need to do is we need to find all of the different sequences where we get 2 side sleepers and 3 people who don't sleep on their side. So for instance, if I label the side sleepers as S, doing S, S, and N would be 2 side sleepers amongst the first 2 people we picked, and then the last 3 people are all non-side sleepers. And it turns out, when you look at these, the various ways to get 2 side sleepers and 3 non-side sleepers, well, there's 10 of those. But each of those sequences, if you think about it, has 2 60% probabilities and 3 40% probabilities. Moreover, the outcomes are all independent. So let's think about how this would work in terms of finding a probability. So what would I do? I would say, well, side sleepers are 60%. Actually, let me go to an equation. So what would I do? I would do 60% 2 times. So 0.60 twice, 0.60 times 0.60. And then 40% 0.40 would happen 3 times. Okay, 0.40 times 0.40 times 0.40. Now, in any of these sequences, we're going to have exactly that probability. Again, we're getting 2 S's, so a 60% twice, and then 3 N's, so 40% 3 times. So each one of these 10 sequences is going to have that probability. So since we have 10 of them, we would just multiply by 10. So we take 10 times 0.60 twice times 0.40 3 times. And by the way, I'm multiplying that because we are independent. So I can just, when we have independent events, we know we can just multiply. And all of a sudden we get 0.2304. Okay, so that's the probability of having 2 side sleepers out of a group of 5 people, 5 randomly selected people. And sure enough, that 0.2304, that was right here, 0.2304, the probability of having 2 people who sleep on their side. Now, here we had basically 5 different spots, and we had to pick 2 spots to put side sleepers. And so I could list out all the sequences fairly easily. But think about what would happen if we had like 10 spots. We were picking 10 people, and I wanted to find out, well, what's the probability of picking 4 that sleep on their side? Well, I would have to know the number of sequences, the number of different ways to get 4 out of 10 in sequence notation. In other words, I'd have to list out all of those sequences. And it turns out that is a huge number, okay? Just calculating that, there's 210 different sequences if we had 10 people and we had to choose 4 to sleep on their side. So there'd be 210. Now that's unreasonable. So what we do is we turn to the calculator, okay? And we're going to turn to both the binomial PDF function and the binomial CDF function. Now the inputs are going to be the exact same. In PDF and CDF, you're going to have an N, that's the number of trials, P, the probability of success on any individual trial, and X, the number of successes. And the binomial PDF is going to give me the probability of getting exactly X successes. The binomial CDF is going to find the probability of getting either X or fewer successes. All right, so that's what we're going to do. We're going to turn to the calculator and find those things. All right, so let me explain where this is on our calculator and how these functions go. But I'm going to do this using an example here. All right, so here's what we're going to do. We're going to do this binomial example. We're going to start with 8 dice. And we're going to find the probability that 3 dice land on the number 5. So here's the experiment. We roll 8 dice. What makes it binomial is we're going to every time look at which one lands on the number 5, okay, meaning 5 up. So first off, let's identify some notation here. We're rolling 8 dice, so n is equal to 8. That's my number of trials. We're looking for the probability. So the probability of success on each trial is landing on the number 5. Now, the number 5 is 1 out of 6 possibilities. So the probability of success on this is 1 in 6 per trial. So here are the first 2 questions. It says, what is the probability that 3 dice land on the number 5? So what that's saying is, what's the probability that X is equal to 3? Okay, probability that X is equal to 3. Now, I'm going to go on to the next question here. I'm going to write that down, and then I'm going to show you kind of where these things are located on our calculator, how to input them, things of that nature. This second one says, what is the probability that 4 dice land on the number 5? So probability that X is equal to 4. Now if I switch the slides, again, I'm going to come back and answer both of those questions, but first off, I wanted to sort of address all of the questions, so I don't have to scroll back to these things. So third question in this same experiment, again, we're rolling 8 dice. It says, what's the probability that 3 or less, probability that the number of successes is 3 or less. So 3 or less dice land on the number 5. What's the probability that 6 or more dice land on the number 5? Now, if you notice again, doing 8 dice rolls and listing out all the sequences, there's just way too many sequences to deal with there. So what we're going to do, turning to our calculator, is we're going to answer these questions. Now, remember what we just said about the binomial situation. if we want X number of successes, then we do a PDF with an N, a P, and an X. So this first problem, we're asking what's the probability that the number of successes is equal to 3? 3 dice land on the number 5. And what we see is that that probability can be found using the binomial PDF feature on our calculator with N. Remember we said N is 8. We're rolling 8 dice. Probability of success is 1 in 6. So you can just type in on your calculator 1 divided by 6. You don't have to put a decimal. And then we're looking for exactly 3 successes. So it's going to be binomial PDF 8, 1/6, 3. Now let's turn to our calculator and see how that goes. So again, this is just me on the screen. And we're looking for the probability that X is equal to 3. So here's our calculator again. And this time we're going to go into the distribution menu. So the distribution menu is right here. You have to hit the second and then this VARS key. Notice the little, on my calculator it's blue, but on your calculator it's whatever the second, it's whatever the color of the second key. So you hit second, distribution. Let's hopefully that comes into focus here. Put the brightness down a bit. Maybe my calculator needs a little bit of brightness adjustment. Hold up. All right, I think I fixed it now. So, brightness adjustment. We're going to just scroll down. So we're in the distribution menu. Again, second distribution. And we're just going to scroll down almost all the way to the bottom, not quite to the bottom. And we see that our binomial PDF and our binomial CDF are letters A and B. So since we wanted the binomial PDF, we're going to click on that one, letter A. And there's 2 options for how this is going to come up. Well, binomial PDF and just the blinking cursor. Hopefully, by the way, you've cleared everything out so you didn't have anything before that. Now, what did we say? We're going to roll 8 dice. The probability of success is 1 in 6. And we're looking for 3 successes. So simply put, my inputs are going to be 8, comma, 1/6, comma, 3. And once you hit enter, you are going to get the following probability, 0.10419044816. And so just like all of our probabilities, we're going to round that to 4 decimal places, 0.1042. So the probability that 3 dice land on the number 5 is 0.1042. Now, just in case your calculator looks different, it turns out that your calculator could have also had the stats wizards on, and if it does have the stats wizards on, your display is not going to do a binomial PDF with a blinking cursor. Your display will look like, first off, it'll say trials, and then lowercase p, and then x value, and then paste. And so you can imagine what that is. In our problem, if your calculator looked like this, trials are 8, probability of success is 1 out of 6, and the x value is 3. So you're just going to type it in like that. Again, depending on what operating system you have, you could have either of these things happen. Paste, and once you paste it, you're going to get the exact same layout and display. So once you've done that, again, either operating system gives you the same exact display. Now, the same thing is going to work also when we have excuse me. So the same thing is going to work also when we have CDF. All right, now that we've seen the CDF, excuse me, now that we've seen the PDF, the CDF works just the same. All right. So let's go on and finish this problem that we've dealt with. So the probability that we said x is equal to 4, probability of 4 successes. Well, we're going to use the binomial PDF. We have 8, still 8 trials, still probability on each trial is 1 in 6, and now we're looking at having 4 successes. Now, one little nice thing you can do with your calculator, if you only changed one number on your inputs, binomial PDF, we just went from a 3 to a 4, I can hit second and then enter, and if I hit second and enter, I'm going to get the same display that I just had. So I can go back, second enter, and go from binomial PDF 8163 and just change that 3 to a 4. If you didn't catch that, that's perfectly fine. You can always retype it in by going back to your distribution menu, second distribution. Okay? And rounding this one to 4 decimal places is 0.0260. Okay? So those are the probabilities of getting 3 or 4 dice to land on the number 5. Now this fourth probability that we see in our example says 3 or less. Well, what did we say about CDF? Oh, X or less successes. So that's exactly in the CDF wheelhouse. Now, if I wanted to do this real shorthand, actually, let's probability that X is less than or equal to 3. So the number of successes is either less than or equal to 3. Now we go binomial CDF. Again, we still have 8 trials. Our probability of success is still 1/6. Automatically does 1/6, but it's going to look like that on your calculator. And then we're looking for 3 or less. Now, by the way, if we had to, oh, geez. The input threw me off there. 8, comma, 1/6, comma, 3. Now again, if you forgot where binomial PDF, or excuse me, binomial CDF is, it's right next to the binomial PDF. It's letter B in the distribution menu. So 8 trials, probability is 1/6 of success, and we're looking at 3 successes or less. So rounding to 4 decimal places, 0.9693. All right. So that's the probability that 3 or less dice land on the number 5. So notice what this is telling us. This is telling us that if we roll 8 dice, having 3 or less dice land on the number 5 is extremely likely, right? And that makes sense to us. If you roll 8 dice, having a lot of them the same number, let alone the number 5, is going to be very improbable. Now, that's kind of what this last one also gets at. It's saying, well, what's the probability that 6 or more dice land on the number 5? So 6 or more. Now, if I was doing this in terms of notation, I'd go probability that the number of successes is 6 or more. 6 or more, greater than or equal to 6. Probability that we have 6 or more. Now that kind of throws a wrench into things because my probability of PDFs and CDFs are X or less. So X or less I can get. X or more, well, how am I going to get that? Well, in short, I'm going to use complements. I want you to think, if you drew a probability distribution, what would the x's be? X would be like 0, excuse me, x's would have been, number of successes would have been like 0, 1, 2, 3, 4, 5, 6, 7, or 8. So these 9 possibilities would have been all of the possibilities. Now we're trying to find what's the probability of 6 or more. So these last 3, 6 or more. Well, if I don't have a nice function to get 6 or more, what I can do is I can look at the complement of 5 or less. So the complement is the probability that x is less than or equal to 5. All right, and we know how to calculate that. That's binomial CDF less than or equal to. We go 8, 1/6, 5. I don't like it when it does that. 8, comma 1, 6, comma 5. I guess I'm gonna have to do it that way. And again, if you're uncomfortable using your calculator or something like that, ask me, rewind the video, but it's pretty straightforward in that case. Again, 2 operating systems, either the one where just the blanking cursor or the one with the trials and then the probability of success and the x value. Now what you'll notice here is that the probability of getting 5 or less is extremely likely. 0.9996. So the probability of getting really low there. Okay. Now that's the probability of the complement, don't forget. So what's the probability of actually getting 6 or more? Well, it's got to be the complement. So take 1 minus 0.9996. Now, if you do this by hand, what's going to happen is you're going to get 0.0004, right? If you did this on your calculator right now, if you took 1 minus, you get some sort of a scientific notation. You get 4.41 e negative 4. And so that scientific notation is just like 10 to the negative 4th. Sometimes we'll get that. We won't get that too often. But don't freak out if you have scientific notation. Just write it as normal scientific notation. If you write this as, 4.41, thought we had that, I'm sorry, times 10 to the negative 4th, that would be okay. Again, that's what the calculator does. If you subtract it, it automatically goes into scientific notation. On a test, I'm going to be okay with this or this. If we're talking about a homework, if it says to round to 4 decimal places, round to 4 decimal places. If it specifically gives you scientific notation to fill it in, and you'll be good. All right. I think there's no problem on the homework that has that scientific notation to fill in. I think it's always round to 4 decimal places. Okay. So here's again a case where our complement tells us what types of, is much easier to calculate, and so it's much easier to deal with. So here's what I'd like you to do. I'd like you to do the exact same thing with this problem. It says, according to Pew Research, 29% of gun owners own more than 4 guns. Assume we select 8 owners at random. Now, be careful here because we're talking about sort of owning guns plus gun owners, so don't get those too confused. So we're selecting 8 gun owners. And we're asking, what is the probability that 2 of the owners own more than 4 guns? What is the probability that 4 of the owners own more than 4 guns? In other words, what's the probability that some of them own more than 4 guns? So we have 2, we have 4. Now that's exactly 2, exactly 4, right? What's the probability that 2 of them? So that question, 3 of them would not work, 1 of them would not work. So what's the probability that exactly 2 out of the 8 own more than 4 guns? What's the probability that exactly 4 out of the 8 own more than 4 guns? And then I want you to try this. Again, selecting 8 gun owners. What's the probability that 3 or less own more than 4 guns? What's the probability that 5 or more of the owners own more than 4 guns? So push pause on the video and go ahead and attempt that, all 4 of those problems. And all 4 of those are on your guided notes as well. All right, so I'm going to go to the guided notes to finish this problem. I'll write down what happens, hopefully in a normal way. Actually, I'm going to go a little bit bigger in my font. All right, so first off, we read this and we immediately see that the number of gun owners that we're selecting is 8, so that's like having 8 trials. The probability of success is 29%, so that's going to be 0.29 as a probability. And the probability of failure is going to be the complement, even though we don't need to write the probability of failure in, I'll still write it down here as an identifying the notation kind of thing, 0.71. Again, they're complements, so you might as well do it. By the way, just as a side note, because they're complements, that's why we don't have to write them all the time in our calculator. Our calculator knows that the probability of failure is the complement of the probability of success, so it just needs the probability of success. All right, so here we go. First question, we should say, well, what is the probability that the number of successes, again, successes is finding a person who owns more than 4 guns. Probability of success is equal, or excuse me, probability that we have exactly equal to 2 successes. Well, exactly equal, we're going to do binomial PDF. Again, PDF is when we have exactly equal. We have 8. Our probability of success is 0.29. And we're looking for exactly 2 successes. So we go to our calculator, second distribution menu, again, binomial PDF. There's going to be 8 trials, 0.29 is probability of success, and then we're getting 2 successes. So what I got out there, again, rounded to 4 decimal places, 0.3017. So the probability that 2 of them have more than 4 guns is 0.3017. Very similar to what's happening in question number 2 here. We say, what's the probability that 4 of them? So all we have to do, again, if you are careful about this, all you have to do is hit second enter. That's sort of the copy and paste version of your calculator. All right, I just copied and pasted on the computer, but on the calculator, the copy and paste of what your previous entry was is second enter. And so 0.1258 rounded to 4 decimal places. Okay. What's the probability that 3 or less own? So we're going to go probability that the number of successes is less than or equal to 3. Less than or equal is binomial CDF. We have 8 trials, probability of success still 0.29, and we're saying 3 or less. Now, one of the things that I do want to mention before I go on is these last two problems, I've said exactly 3 or less, but realize something that we could rephrase this to say less than 4. Less than 4 is 3 or less, all right? So if it said less than 4, instead of 3 or less, then we would have had to have done the exact same thing. So hopefully you get what I'm saying by that. But the basics of it is that be very careful and attentive to how the English language is being played out there. All right, because subtle changes, we can see less than 3 is not the same thing as 3 or less. Less than 3 would be less than or equal to 2. So 3 or less than 4. Less than 3 would be 2 or fewer. Okay, hopefully that all makes sense. And then lastly, what's the probability that 5 or more of them own more than 4 guns? Again, I like to write this down, but think 0, 1, 2, 3, 4, 5, 6, 7, 8. Again, we're trying to select 8 gun owners. 5 or more of them would be 5, 6, 7, and 8. So we kind of separate that group out, and we say, oh, the complement is the probability that x is less than or equal to 4. So we can find a binomial CDF on that one. 8, 0.29, 4. Type that into our calculator, 0.9495. I'm going to increase that font a little bit. There we go. So probability of that, again, don't forget that's the complement. So when it says we're trying to find the probability, scroll down here, that x is greater than or equal to 5, we just take 1 minus that number, and we end up with 0.0505. So the probability that 5 or more own more than 5 guns is fairly rare. It's about 5% of the time. But 3 or less own more than 4 guns. That's a pretty common occurrence, 0.82, right? 82% of the time. That's a pretty common occurrence. All right. What I'd like you to do is I would like you to read and do the following questions all according to the roulette wheel. So I'm going to I'm going to look at this question, again, read that question, read the next question, so one says we're going to roll 25 times in a row, other is 75 times. So push pause and do those two problems. All right, just to remind you why I keep saying push pause and do these problems, because in a normal classroom setting, that would be the time that I give you to work on the problems, to do them on your own, to walk around the class and help and things like that. So that's what we would do in a normal classroom setting. Let's go back to the first roulette problem. And you know what? I'm going to go to the guided notes version of this. Okay, so it says red is 18 out of 38, and we're going to assume we bet 25 times in a row. Now, if I'm given that situation, betting 25 times in a row means there's 25 trials. N equals 25. Well, what's the probability of success? Well, probability of success is simply 18 out of 38 because our success is looking for a red. So what is the probability that 13 or more of our bets win? Now, here's what's significant about that. 13 means that we win more than we lost, right? If I bet 25 times, 13 means I won more times than I lost. And if you know anything about roulette, if you win 12 or fewer times, you lost money. If you went 13 or more times, then you win money. So in other words, what we're doing is we're finding the probability that we win money, right? You don't have to write that down. This is the example. So what is the probability that our success is 13 times or more? Now, I'm not going to write this down like I did last time, but you can imagine writing 0, 1, 2, all the way up to like 12 and 13, 14, and then it keeps going all the way up to 25, right? That's the number of successes. I'm not going to write every one. Those dot, dot, dots will just be placeholders. But 13 or more, we can separate out. We can say, well, I can't have a function that does 13 or more, but the complement is the probability of winning 12 or less. All right, so I can find that by doing binomial CDF. Again, we're doing 25 trials here. The probability of success is 18 over 38. And we're saying 12 or less. So that's just something I type into my calculator, as always. And I didn't type it into my calculator yet, but I should have. 25, 18 out of 38, and 12. I got 0.6049. 0.6049. So again, remember, don't forget we weren't trying to find actually the probability of getting less than or equal to 12. We were trying to find the probability of more than or equal to 13. So probability that x is greater than or equal to 13. Take 1 minus that, 0.3951. All right, so the probability of getting 13 or more is 0.39451. Excuse me. Notice that that's well under 50% of the time. So your probability of losing money is much higher than your probability of winning money. But since we did it 25 times, it's like a 60-40 kind of split. Okay? By the way, if you do it one time, it's like a 47-53 type split. Let's see what happens when we bet 75 times. And again, notice that 38 or more of our bets winning means that this is the same sort of probability example. In fact, I'm going to copy and paste most of this. I thought we had. So the probability that we win, let me make this a little bit easier to see. All right, sorry about that. Copied all those dots. So the probability that we win this time is the probability that we win more than half of the roulette wheel, the roulette rolls. So more than half of 75. If you go 75 divided by 2, that's 37 and a half. So 37 means we've lost money. 38 means we've won money overall. Similar situation. Instead of going up to 12, we're going up to 37, and then the 38 to 75 options are there. So complement of 38 or more is less than or equal to 37. So we have to change our n. Our n now, we're rolling 75 times. However, the probability of success is we're still getting 18 out of 38 because success is still red. We want 37 for my binomial CDF. So all I have to do is change that 25 to a 75, that 12 to a 37, and we get 0.6764. Notice that went up by a few percentage points. And that means that the probability of winning money actually went down by a few percentage points. It went from 0.3951 to 0.3237. So by this example, we see two things. First off, we see the power of complements and doing all that stuff, just like we saw in the previous examples. But we also see this idea, whoops, I forgot to write 38 there, I apologize. We also see this idea that if you're going to win money, you actually have a higher probability of winning money, even though it's less than 50%, playing the roulette wheel less times. In other words, the more you play, the higher chance that you have of losing money. All right. So that's the roulette example of that. And by the way, what's that tell us? That tells us that if you're thinking about making your retirement plan, basically playing roulette at the casino, and you're going to play it all your life, when this N goes up really, really high, this chance of losing goes up really, really high, and this chance of winning more than you've lost goes up really, really low, or excuse me, it goes down to really, really low values. So the more you play, the higher chance you have of losing money. Okay. Now, again, you don't get wiped away every time, but that's the way it goes. So that is the probability. Or excuse me, that's how we calculate probabilities with binomial distributions. And if we wanted to, scrolling back to what we started on, we could, for every single one of these, we could have typed out and created a really big probability distribution using binomials where we calculated every single one of these probabilities. Okay. Now, what were the other things we did with the binomial, excuse me, with the probability distributions? We also found the average. And there's two ways we found the average. One was by taking this table and inputting it into our calculator. 0 through 5 goes into list 1. All of these corresponding probabilities go into list 2. And then do one variable stats, list 1, comma list 2, or class list 1, frequency list list 2, probability list 2, those types of things. So we could have done that way. We could have also taken this table and went multiply, 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 and then add them all up, right? Multiply every single x by its corresponding probability, and then add it all up. So those were the two methods we found in the last section. Now that gets really cumbersome if we're talking about rolling a roulette wheel 75 times in a row, right? That means my distribution would have had to have possibilities from 0 all the way up to 75 if I wanted to find the average and the standard deviation as well. It turns out that with the binomial example, we have a nice shortcut for finding the average and standard deviation. And it's the following. The average, or the expected number of successes in a binomial distribution, can be found by just taking n times p. And the standard deviation, remember when we dealt with probability distributions, we always had to use population standard deviation because we didn't have sample standard deviation for probabilities. Well, that can be found by just taking the square root of n times p times q. Now, one thing I want to mention before I move on is that on this test over chapters, especially when you're dealing with this chapter, chapter 4, that standard deviation and mean, those aren't formulas that we have to memorize. Those will be on some sort of a formula sheet that you get. The same thing, what will be on a formula sheet, you'll see something like this. It'll say binomial probability, binomial PDF NPX. You'll have to know what the NPX stands for, but at least you'll get the order of input. And again, binomial PDF, binomial CDF, okay? A lot of calculators that just have binom PDF, binom CDF, but the point is those will be on a formula sheet. And if you click in the practice test version, you will see the formula sheet. So on Moodle, when you click on the practice tests, you'll see the formula sheet in there, in that folder. Well, this makes it really nice to find means and standard deviations. So when we have binomial distributions, to find a mean standard deviation, we can just take these two formulas. Again, these two formulas, along with binom PDF, binom CDF, will be listed on a formula sheet when you're going through these things. So let's go back to our 3 experiments that we did. Let's start with the 8 dice example. So we're going to roll 8 dice, and we're going to see how many 5s we would expect to see on the dice. And then we're going to ask, well, what's the standard deviation of this scenario? So again, I'm rolling 8 dice, and I'm looking for 5s. So what we would do, we would say, excuse me, well, the expected number of successes, again, the way we type this, expected number of successes, E of x, is going to be the average number of successes. Since we're rolling 8 dice, my n is 8. Since the probability of success is 1 out of 6. Again, rolling a 5 has a probability of success on each trial of 1 in 6. And so that's it. That's the average. The average number of successes is 1.33. Okay? Or the expected number of successes is 1.33. So you expect to get a little over 1 success when we roll 8 dice, meaning success meaning number 5. So you expect to get a little over 1. Now, remember what expected value meant? It doesn't mean we'll ever land on 1.335s, right? That would not make sense at all. You either land on 1 or 2 or 3 or 4, but you never land on 1.33. What that expected value means is that if you rolled 8 dice and I rolled 8 dice, and we had 500 friends roll 8 dice apiece, and we took all those and we averaged them all up, it would probably average to about right about 1.33. Some people will get 0, some people get 1, some people get 2, some people might get 3, but it all would average out in the end to about 1.33. So that is how we would calculate. Again, it's just taking n times p. So expected number of successes, 1.33. Now standard deviation, similar. Yeah, that was gonna put me on. Standard deviation. Well, this is, don't forget, this is always a population standard deviation. So we can look at our population standard deviation, and it says it is the square root, find the square root symbol, square root of n times p times q. Now, what is n and p and q in this situation? Remember, n, number of successes, good. Probability of success, we just said that was 1 in 6. And then the probability of failure. Whoa. Let me actually rewrite this. Now, one thing I do want to mention, I'm putting these things in parentheses just so it's sort of easier to see. When I type it into my calculator, I'm just going to put 1 divided by 6 and multiply in there. And I'm going to put, well, if 1/6 is the number of successes, probability of successes, then 5 out of 6 is the probability of failure. Again, that's on each trial. But the one real clear thing we have to always be aware of is that when you type this into your calculator, the 1/6 and the 5/6 both need to be underneath the square root symbol. Now, if you have the math type calculator, that's pretty easy to see. Sometimes if you don't have the math type calculator, if you have the other type of calculator, I say math type, it's just the way you see it. You have to just make sure that parentheses ends in the right spot. So in any case, sorry to take that aside, our population standard deviation is 1.50. Okay, again, make sure your probability of success and probability of failure come under the square root. All right, so that's how we calculate it. Again, we'll just use those formulas and calculate it. So what I would like you to do is go back to another example we did. We did the gun owners example. I want you to calculate the expected number of gun owners who own more than 4 guns and calculate the standard deviation of this scenario. Push pause on the video. All right, so hopefully you did that. Hopefully you took and you calculated that. I'm going to go on the guided notes here. Go back to the guided notes. Expected number of gun owners who own more than, well, that's going to be, we are selecting 8 of them, and each of them has a 0.29 chance of owning more than 4 guns. So about 29% of the 8 we would think own more than 4 guns. And so that would come out to about 2.32. All right. And similarly, standard deviation, we just use that formula once more. So we say standard deviation. Again, don't forget, this is always the population standard deviation. Population standard deviation is going to be the square root of 8 times 0.29 times 0.71. Again, that 0.71 comes out of the fact that the probability of success being 0.29 means that the probability of failure is the complement, or 0.71. Again, that's success and failure for each trial. And so we get a standard deviation of 1.28, again rounded to 2 decimal places. So notice how much easier that is than actually having to create a probability distribution and table and then do all of that work. So it's a really, really nice shortcut when it's available to us. I want you to also do this next one. Find the mean and standard deviation when we bet 25 times on the roulette wheel. All right, so hopefully you've done that. So, and one of the things about this, oh, excuse me. I'll find the mean first. So, one of the nice things here, once you get really used to the formula, it's pretty easy formulas to remember. Again, you're not going to have to remember them, but I do, so no big deal. So 25 multiplied times 18 over 38, n times p, that gives me expected value of 11.84. Notice that 11.84 is under what would win me money, right? We would expect less than half of our rolls to be successes. And then again, standard deviation would be square root 25 times 18 over 38 multiplied times 20 out of 38. Again, I'm using complements there. 18 out of 38 is a complement of 20 out of 38. Excuse me. And this one is 2.4965, blah, blah, blah. That would round up to 2.50. Okay. So there you have it with the mean and standard deviation of binomial distributions. All right. Binomial distributions have these really nice means and really nice standard deviations. Now, how this is going to look like on a test or on a homework scenario, it's going to look like this. Let's go back to the ISIS example. And again, we're going to say 6% of Palestinians have a favorable view of ISIS. At least that was according to the poll in 2015. And we're going to select 5 Palestinians at random. So what a normal problem would look like is it'd have a few probability questions, and then it would have like an expected value and a standard deviation. So it all would be all confined within the exact same questions. So what I'd like you to do is I'd like you to try to complete this problem. Push pause on the video and then come back and complete it. All right, so hopefully you did that. I'm going to do these fairly quickly so that we can move on to the next thing. So first one, we asked for the probability of exactly one success. So exactly one, we're going to do probability. Since this is a binomial experiment, binomial PDF. We have we're picking 5 Palestinians. Each one has a 0.06 probability of success, meaning liking I6. And we're finding what's the probability that one success there. And what I got is 0.2342. This second one, a little bit different because it says at least one. So what I have to do, again, to find this, I first off have to say, well, at least one means 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5. What's the complement? Well, the complement is going to be the probability that either 0 or fewer have a favorable view of ISIS. Okay, and so CDF 0 or fewer, binomial CDF. By the way, PDF would have also worked because 0 or fewer are just exactly 0. So what would that be? 0.7339. Now again, that's the complement. So if I wanted to find the probability that at least one has a favorable view of ISIS, I would subtract that and I get 0.2661. Okay. By the way, remember how we did that previously? Previously, we used independent multiplication to do that. And now we can see we can use binomial CDF to accomplish the exact same goal that we had from before. All right, expected number. This takes longer to write than it does to actually explain. We just say, well, the expected number of successes is going to be n times p. In this case, my n is 5, and my probability of success is 0.06. And so the expected number of successes is 0.3. Notice that, again, 0.3 isn't going to make sense for any individual experiment, but for a collective, it can average out to about 0.3. And then lastly, standard deviation is going to be square root of n times p times q. Again, make sure the p and the q, in this case the 0.06 and 0.94, are both underneath the square root. And if we did that, I got 0.531. Well, actually, since it's a standard deviation, I can just round it to 2. I'll just round it to 0.53. Okay. Again, typically anything mean, standard deviation, around to 2. All probabilities, I either go to 4 unless I have some sort of a big scientific notation in which I write the scientific notation. But there you go. That's a typical problem. Typical problem from this of this part of chapter 4 is that we'll deal with binomial examples, which we calculate some probabilities and then do the mean and standard deviation. Now, I want to re-emphasize what was so interesting about the binomial example, because in the next part of the chapter, we're going to switch things up a little bit. And we're not going to have a binomial experiment in the next part. Again, I emphasize a lot of different scenarios can be thought of as binomial experiments, but not every scenario. So binomial experiments, we have to have a fixed number of trials before we ever start. Each trial has to either be success or failure. All the probabilities are constant and all of the outcomes are independent. So if I have those 4 key points, then I can use all the tools that I showed. All right, so that ends this video for 4.2, and we'll start 4.3 next time.